So far we've been talking about assembly instructions, and ultimately what has to be provided to the hardware is a string of 32 bits for each instruction, right? So now I'm going to tell you what the format for that instruction is. For the most part, you will not be converting assembly instructions into the string of 32 bits. Okay, but these are the formats for those instructions. Now we've seen two broad classes of instructions. One is the R-type instruction that has 3 register operands. So the way these instructions are represented, you have a 6-bit opcode, right, which maybe tells you that this is, doing an add or doing a sub and so on. Then you have space for these 3 register operands. So you have 5 bits for the source, 5 bits for the second source, and then 5 bits for the destination register. And I need only 5 bits to represent a register because I have only 32 registers. So 5 bits is enough to tell me that I refer to one of these registers between 1 and 32. Once I've done that, I also have 6 bits at the very end to represent the function. This is usually describing the variation on the add operation, right? So I may be adding a byte, I may be adding 2 bytes, a word, a 4-byte word, and so on. So the 6-bit function basically tells you, what kind of wrinkle is this on this particular operation over here. Then I also have 5 bits allocated over here for the shift amount. So this is specific to instructions that shift the value either left or right. So there's shift left logical, there's shift right logical. We will get to examples of these shortly as well. But these instructions are essentially shifting the value in a register to the left or the right. And this field over here tells me by what amount am I shifting this value to the left or the right. The second kind of instruction is this I-type instruction. Examples of this include our immediate operations. They also include, loads and stores, right? And these instructions only have one register operand. So essentially you have 6 bits to specify the opcode, that is, what kind of instruction is this. Then you have 5 bits for one of the source registers. You have another 5 bits for the second register operand. So in case of a load word that I'm showing over here, there are 2 register operands. Those are specified in RS and RT. And then I have this number 32, which is the offset I want to add to my base address. That offset is provided in this next field over here, right? So you have room over here for a 16-bit constant. If you were using an immediate add instruction, you have 2 register operands, and then you have an immediate value. So the 2 register operands are encoded in RS and RT, and the immediate value is encoded into the 16-bit space that stores the immediate or the constant value. So here are a few other instructions. We just talked about shift left and shift right. What it takes is a value sitting in a register and then moves it to the left or the right. So if the value sitting in this register was 101, which is the number 5, and then a bunch of zeros before it, if I shift it to the left by 1, what I get is the value 1010 and then a bunch of zeros before it. Why is this useful? This is essentially a multiplication of the number by 2. So 1010 is essentially 10. So shifting to the left is the same as multiplying by 2x. If you shift it 2 places to the right, that's the same as multiplying it by 2 squared. That's multiplying by 4. Shifting it 3 places to the right is the same as multiplying by 2 cubed. And similarly, shifting it to the right is like division, right? So if this value was shifted to the right by 1, I get 101, which is 10 divided by 2. Okay, so shifting 1 place to the right is the same as dividing by 2. Shifting 2 places to the right is the same as dividing by 4. Then you can also have bitwise AND, bitwise OR, and bitwise NOT, and there are special instructions for each one of those. Now I'm going to introduce a new kind of instruction, which is the control instruction, which allows you to jump back and forth in the program. And there are multiple instructions that allow you to do that. The first kind of instruction is a conditional branch, which says that, depending on a certain condition, I want you to jump to a certain instruction in the program. Okay, and instructions are going to be denoted by labels, in this case label L1, in our programs. Okay, now ultimately, the compiler and the assembler are going to convert these labels into actual 32-bit strings, which refers to the specific address of that instruction. Okay, but when you're writing an assembly, you will typically use a label, and you will leave the calculation of the 32-bit string up to the compiler and the assembler. Okay, so the first example of a control instruction is branch on equal to, which says that if register 1 and register 2 are equal, then I want you to jump to label L1. If they're not equal, then you won't jump to label L1, and the next instruction that you'll execute is the instruction that comes right after. Okay, so if you do branch on equal to, $S1, $S2, and then L1, and then you have an instruction here, so on, and then finally you have an instruction down here which is labeled L1. Okay, so if S1 and S2 are equal, then you jump straight here, and the next instruction you'll execute is this one over here. If S1 and S2 are not equal, then the next instruction you execute will be the one over here, followed by this, and so on. Okay, and then similar to branch on equal to, you also have branch on not equal to. So it does the exact opposite of what branch on equal to does. That is, if S1 and S2 are equal, then it'll just move on to the next instruction, right? So if you do branch on not equal to S1, S2, L1, then if S1 and S2 are not equal to, then you jump to L1. If they're equal, then you just move on to the next instruction here. And then in addition to these two instructions, you also have a special instruction that is set on less than, which is not itself a branch instruction, but it sets a certain value based on a comparison of two registers. Okay, and we will see an example of this later, right? So you essentially need to do a set on less than, and then follow it up with a branch instruction that looks at the result of the set on less than. The second kind of branch instruction is an unconditional branch, which says that I don't really need to compare two values. I know I need to jump to a different instruction, and so I'm directly going to jump there. If the compiler knows exactly where you're jumping, then you encode that as part of the instruction, right? So the instruction says jump to a certain address. When you're writing the assembly code, you will specify that address as a label, and the compiler will essentially convert that label into a given address. If the compiler does not know where you want to jump to, then at runtime, you're going to figure out where you need to jump to, and you're going to store that address in some particular register, and then you're going to jump to the address specified in that register, right? So JR with a register operand tells you exactly where you need to go to. Okay, so now that you've seen these examples of branch instructions, let's look at an example that I'm showing you over here. So what I'm trying to do over here is take a very simple if then else statement and convert that into assembly code. Okay, so let's just show you the solution and walk through it. So let's assume that I and J are already sitting in registers S3 and S4. So I'm going to compare the values in S3 and S4. If they are not equal, right, then I need to execute the else part. So there's a label down here which says else, which is going to execute this part over here. So maybe let's just look at that code here. So G and H are already in registers S1 and S2. So here I do a subtract of S1 and S2, put it into S0. If these two values are indeed equal, then I won't jump to the else part, and I'll start executing the very next instruction, which is executing the then part. So I add S1 and S2 and put it into S0. Once I'm done, I need to go to whatever piece of code was sitting down over here, right? In fact, both the then part and the else part, once they are done, need to execute this instruction next, right? And so that instruction has a label exit. And once I'm done with the then part, I'm just going to jump straight to that exit location. The else part, after it finishes this instruction, is going to default to executing the next instruction, which anyway happens to be this exit label. So these 4 lines of code are essentially used to represent this bit of original, say, C code. Now let's look at one more example just to better understand these control instructions. So in this case, what I'm doing is going through a while loop. I'm incrementing I each time I go through the while loop. That means I'm essentially scanning through this array called save, and I'm looking for an entry that has the value k. Okay, so we'll assume that I and k are in S3 and S5, and the base of array save is in register S6. Okay, so this is what that code is going to look like. So firstly, I have a label to the start of this loop, right? So every time the condition is not met, I have to jump back to the start of the loop, right? And that's what this one is doing over here. It says, jump to the top of the loop. When you get to the top of the loop, the first thing I need to do is get the value in save I. Okay, and how do I do that? I need to basically multiply I by 4 and add it to the base address for save 0. Okay, so let me say that one more time. So we know that the address of save 0 is in $S6. Okay, save 1 is basically $S6 plus 4. Okay, the address of save 2 is $S6 plus 8. And likewise, the address of save I is $S6 plus 4 times I. Okay, since I is in S3, I want to first multiply S3 by 4. And the easiest way to multiply by 4 is by shifting that value 2 places to the left. So I do shift left logical. I take the value in S3 and shift it to the left by 2. That gives me 4 times I. And that's now being saved in temporary register T1. Okay, if I add that to the base address S6, I now get the address of save I. Okay, so I take S6, add T1 to it, and keep it back in temporary register T1. Okay, so now I have the address of save I. So I just have to load word from address that is in T1. I get the value sitting in that address and I put it into register T0, right? So now I have the value of save I. Now I'm going to compare that value to K, which is in S5. And so I do a branch on not equal to T0 and S5. If T0 and S5 are not equal, then I jump to this exit location, right? So basically you're in this loop while the contents of array save equals the value K, right? I think I may have said the exact opposite when I was introducing this example, but essentially you're in this loop while save I is K. Okay, so if they happen to not be equal, then it's time to exit the loop. So then I jump to exit. If they're equal, then I'm not going to do the jump. I'm going to execute the next instruction, which essentially says that I need to stay in this loop. But before I jump to the start of the loop, let me increment I by 1, right? So I being in S3, I'm going to add 1 to it, and then I'm going to jump to the start of the loop again. So this is a more detailed example and a more non-trivial example that shows you how these control instructions work.